Imagine standing in the middle of Tokyo, completely unaware that 70 meters beneath your feet, an underground structure larger than many skyscrapers is quietly waiting for the next flood. It doesn't stop floods with walls. It doesn't block rivers. Instead, it captures entire rivers underground before they can destroy one of the world's largest cities.
Every civilization leaves a mark. These are the echoes of power.
Tokyo is one of the most densely populated metropolitan areas on Earth. More than 30 million people live across the greater Tokyo region. Millions travel through its rail network every day. Countless businesses depend on uninterrupted transportation. Yet beneath this modern megacity lies a constant threat. Not earthquakes, not volcanoes, water. Every year, powerful typhoons sweep across Japan, bringing extraordinary rainfall in just a few hours. Small rivers rapidly overflow. Concrete streets prevent rainwater from soaking into the ground. Water rushes toward low-lying neighborhoods faster than traditional drainage systems can handle. For decades, flooding caused billions of dollars in damage, disrupted transportation, and threatened millions of residents. Japanese engineers realized that building higher flood walls alone would never solve the problem. There simply wasn't enough space above ground. So they looked in the only direction left: down. What they built would become one of the greatest underground engineering projects ever completed. A hidden hydraulic megastructure designed to intercept floodwater before it ever reaches the city. Today, it quietly protects millions of people. Most of them never even know it exists. Tokyo's flood problem isn't caused by a single river. It's caused by geography, climate, and rapid urbanization working together. The metropolitan region is crossed by dozens of rivers and drainage channels, many of which were originally small natural waterways. As Tokyo expanded into one of the world's largest cities, forests and farmland gradually disappeared beneath roads, buildings, and concrete. Rainwater that once soaked naturally into the soil suddenly had nowhere to go. Instead, it rushed across hard surfaces, entering rivers almost instantly. During an ordinary storm, this isn't a major problem. But during a typhoon, everything changes. Some areas can receive months of rainfall in only a few days. Water levels rise with astonishing speed. Small rivers become dangerous torrents. Once one river exceeds its capacity, neighboring rivers begin experiencing the same pressure, creating a chain reaction across the city. Traditional engineering solutions offered only temporary relief. Higher levees required more land. Wider rivers meant demolishing thousands of buildings. Building additional reservoirs inside one of the world's busiest cities was nearly impossible. Japanese engineers eventually reached a remarkable conclusion. Instead of expanding outward, they would expand downward. Deep beneath Tokyo, they envisioned an enormous underground network capable of collecting excess floodwater from multiple rivers before those rivers overflowed. Rather than forcing every river to become larger, they would temporarily move the flood itself beneath the city. It was an idea unlike anything ever attempted at this scale. But turning that vision into reality required engineers to solve an even bigger challenge. How do you capture an entire river and send it underground? Capturing floodwaters sounds simple. In reality, it's one of the most difficult problems in hydraulic engineering. Floodwater doesn't arrive at a constant speed. It accelerates, changes direction, carries trees, mud, vehicles, and enormous amounts of debris. Engineers couldn't simply dig one giant tunnel and expect everything to work. The water first had to be intercepted safely. Across northern Tokyo, several flood-prone rivers were connected to an entirely new underground network. When river levels reach a predetermined height, massive intake structures automatically begin diverting excess water. Not all of it, only the amount needed to prevent the river from overflowing. This is a critical engineering principle. The rivers must continue flowing naturally, while only dangerous floodwater is redirected underground. To accomplish this, engineers designed enormous vertical shafts, some nearly 70 meters deep. Imagine standing inside a building over 20 stories tall. then turning it upside down beneath the ground. That's the scale of these shafts. As floodwater enters, gravity does almost all the work. The water spirals downward through the cylindrical chamber, converting destructive surface energy into a controlled vertical flow before entering the tunnel system. This dramatically reduces turbulence and protects the underground infrastructure from violent hydraulic impacts. Each shaft acts like a giant pressure regulator. Without them, floodwater would enter the tunnels with enough force to damage the entire system. But collecting the water was only the first challenge. Now engineers had to move millions of tons of it beneath one of the busiest cities on Earth. Once floodwater enters the vertical shafts, its journey is only beginning. Hidden beneath the suburbs of Tokyo is a network of enormous reinforced concrete tunnels stretching for more than 6 kilometers. These aren't ordinary drainage pipes. They're large enough for maintenance vehicles to drive through. Each tunnel was excavated deep below existing roads, railways, homes, utility networks, and critical infrastructure. Engineers couldn't risk disturbing the city above. That meant every meter of excavation required continuous monitoring. Ground settlement, soil pressure, groundwater intrusion, and tunnel alignment were measured constantly throughout construction. Even a few millimeters of unexpected movement could affect buildings on the surface. The tunnels were designed with a carefully calculated slope, not steep enough for water to become dangerously fast, not too flat, where sediment would begin accumulating. Instead, gravity carries floodwater efficiently toward the heart of the system while maintaining a stable flow velocity. The concrete lining also plays a crucial role. It must withstand tremendous hydrostatic pressure while resisting decades of chemical erosion caused by fast-moving water and suspended sediment. This hidden tunnel network quietly links multiple rivers together, transforming separate flood problems into one controlled hydraulic system. But all of that water still has to go somewhere. And that's where engineers built the most extraordinary structure of the entire project. At the end of the tunnel network lies a chamber unlike anything most people have ever seen. Officially, it's a pressure adjustment water tank. But around the world, it's known by another name: the underground flood cathedral. The chamber stretches nearly 180 meters long. Towering concrete columns, each weighing hundreds of tons, support the massive ceiling above. Standing inside, it feels less like an engineering facility and more like an ancient temple built for giants. But every column serves a precise engineering purpose. When floodwater races through the tunnels, it carries enormous momentum. If that water were pumped immediately, pressure fluctuations could damage pumps, tunnels, and downstream infrastructure. Instead, the chamber slows everything down. Water spreads across the enormous reservoir. Flow velocity decreases. Turbulence is reduced. Pressure equalizes throughout the system. Hydraulic engineers call this energy dissipation. It's one of the most important stages of the entire operation. Only after the water becomes stable can the final phase begin, moving millions of tons of floodwater back into the Edo River using some of the most powerful pumping equipment ever installed beneath the city. Collecting floodwater underground is only half the mission. Eventually, every drop must leave the system. But there's one problem. The underground reservoir sits lower than the Edo River. Gravity can bring water into the system, but it can't push it back out. That responsibility belongs to one of the most powerful pumping stations ever built beneath a city. Inside the facility, enormous gas turbine-powered pumps stand ready around the clock. Together, they generate roughly 14,000 horsepower, producing enough force to move around 200 cubic meters of water every second into the Edo River. To understand that scale, imagine filling an Olympic-sized swimming pool in only a few dozen seconds. That's the amount of water these pumps can move during a major flood event. But raw power alone isn't enough. If every pump started at full capacity simultaneously, the sudden pressure surge could damage tunnels and create dangerous hydraulic shocks. Instead, engineers use automated control systems. Water level sensors continuously monitor the storage chamber. As floodwater rises, the pumps start one by one. Their speed changes automatically, depending on incoming flow. If rainfall suddenly increases, additional pumps join the operation. If water levels begin falling, the system gradually slows down. Every decision is based on live hydraulic data. The goal isn't simply to pump water away. It's to maintain a perfectly balanced flow throughout the entire network. Because in hydraulic engineering, control is often more important than power. Yet even with enormous pumps, the entire system would fail without one invisible component: the intelligence that decides when everything should operate. Modern flood protection doesn't begin with concrete. It begins with information. Long before a typhoon reaches Tokyo, weather satellites begin tracking its movement. Meteorological radars measure rainfall intensity. River sensors monitor changing water levels. Ground stations record atmospheric pressure, wind speed, humidity, and soil saturation. All of this information flows into centralized control centers. There, powerful computer models simulate how rivers are expected to behave over the next several hours. Engineers don't simply react to flooding. They predict it. If forecasts indicate extreme rainfall, operators can lower water levels in connected rivers before the storm arrives. The underground reservoir is prepared. Pumping equipment is tested. Emergency power systems are verified. Maintenance crews move into position. By the time the first heavy rain reaches Tokyo, the flood control system is already waiting. This approach is known as predictive flood management. Instead of responding after streets begin flooding, engineers create storage capacity before rivers overflow. Every decision happens in real time. Thousands of sensor readings, weather forecasts, river models, and hydraulic calculations work together like one giant digital nervous system. To most residents, none of this is visible. They simply wake up after the storm and continue with their day, never realizing that an invisible engineering network quietly prevented a disaster beneath their feet. But no engineering system lasts forever. Keeping this underground giant operational requires another challenge that few people ever see. When the floodwater disappears, the engineering work is far from over. Every major operation is followed by detailed inspections. Maintenance teams enter the tunnels searching for sediment buildup, concrete wear, steel corrosion, and damage caused by debris carried by floodwater. Even small cracks receive immediate attention, because under repeated hydraulic loading, tiny defects can eventually become major structural problems. The giant intake shafts are also inspected. Mud, branches, plastic waste, and even abandoned vehicles can be carried into the system during extreme floods. Specialized equipment removes accumulated debris before it can reduce flow capacity. Engineers also inspect the massive pumps. Bearings are lubricated. Turbine components are tested. Backup generators are exercised under full load. Every sensor is recalibrated. Every emergency communication system is verified. The goal is simple. When the next typhoon arrives, nothing can be left to chance. Unlike a bridge or skyscraper, a flood control system may sit idle for weeks. But when it's needed, failure isn't an option, because millions of people depend on equipment they may never even know exists. And that raises one final question. As extreme weather becomes more common around the world, could other countries build underground flood control systems like Tokyo's? Or is this engineering masterpiece unique to Japan? Tokyo's underground flood control system is often described as a miracle of engineering. But is it something every country can build? The answer is both yes and no. The engineering principles are universal. Temporary flood storage, gravity-driven tunnels, pressure regulation, high-capacity pumping, real-time monitoring. These concepts can be applied almost anywhere. But building a system like Tokyo's requires far more than technical knowledge. It requires space beneath the city, stable geological conditions, long-term government planning, and billions of dollars in investment. Many older cities simply don't have that luxury. Underground transportation systems, utility tunnels, subways, and deep building foundations already occupy much of the available underground space. Retrofitting an entire flood control network beneath an existing city can become more expensive than building it from the beginning. That's why many countries are combining different engineering solutions. Some expand rivers. Others create underground storage tanks. Many are restoring wetlands that naturally absorb floodwater. Singapore uses massive drainage canals linked with reservoirs. The Netherlands relies on floodplains, pumping stations, and movable storm barriers. The United States is investing in larger stormwater tunnels and smart drainage systems in several flood-prone cities. Every country builds differently, but the engineering philosophy is becoming remarkably similar. Don't wait for floods to happen. Prepare the city before they arrive. And perhaps that's Tokyo's greatest contribution to modern engineering. Not a specific machine, not a specific tunnel, but a completely different way of thinking about flood protection. Climate scientists expect extreme rainfall to become more frequent across many parts of the world. At the same time, urban populations continue growing. More buildings, more roads, more concrete, less natural ground to absorb water. That combination places enormous pressure on traditional drainage systems. Future flood protection will likely depend on intelligent infrastructure rather than simply larger infrastructure. Engineers are already developing AI-assisted flood prediction models capable of analyzing millions of data points in real time. Digital twins allow entire cities to simulate incoming storms before the first raindrop falls. Smart floodgates automatically adjust based on river conditions. Pump stations continuously optimize energy consumption while maintaining maximum flood capacity. Some researchers are even exploring autonomous drainage networks capable of making hydraulic decisions without direct human intervention. The goal isn't simply moving more water. It's moving water at exactly the right place, at exactly the right time. Tokyo's underground system represents an important step in that evolution. It proved that flood protection doesn't always need to be visible. Sometimes, the safest infrastructure is the infrastructure no one ever sees. As cities continue expanding, future engineers may spend less time building upward and far more time building beneath our feet. Every year, millions of people walk through Tokyo without realizing what exists beneath them. They board trains, drive to work, visit restaurants, shop in crowded streets, completely unaware that an engineering masterpiece lies 70 meters below, waiting, not for tourists, not for attention, but for the next storm. The greatest engineering achievements are often the ones we never notice, because when they succeed, disasters never happen. Tokyo's underground flood control system doesn't eliminate nature. It doesn't stop the rain. It doesn't prevent rivers from rising. Instead, it quietly guides one of nature's most destructive forces through a carefully engineered path. That may be its greatest achievement. Not defeating water, but understanding it. As climate change reshapes cities around the world, the question engineers face is no longer whether floods will come. They will. The real question is whether our cities are prepared when they do. Japan answered that question by building one of the most extraordinary underground hydraulic systems ever constructed. A megaproject hidden beneath millions of people. Invisible, until the moment it becomes absolutely essential. This is Echoes of Power. If you enjoyed discovering the engineering hidden beneath one of the world's greatest cities, subscribe for more documentaries exploring megaprojects, real engineering, and the innovations shaping our future. Because beneath every great civilization, there is even greater engineering.